normal homework assignment. All right, the traveling salesman problem. If you recall, we have talked about two methods for solving the traveling salesman problem. One is brute force. And what's good about brute force is another one. Always gives the best answer. Remember, the whole idea of the traveling salesman problem is you're trying to find a Hamilton circuit with the smallest total weight if you add up all the weights, right? When you do the brute force, that is, you just write down all possible Hamilton circuits and add up the weights for all of them. This always gives the best possible answer. That's a good thing, but is basically impossible to do on any kind of large real life example, realistic sized example. Way too many things to check. Takes forever. Even if you're using a computer, this is not the way to do it in the real world. You can do it by hand or using a computer for small examples. And I probably, on our final exam, I probably will ask you to do a small example of the brute force just to see that you know how to do it. But in the real world, you don't do it this way. Actually, I am sorry to say, I said something slightly incorrect about the brute force algorithm last time. I don't know if anybody noticed, but somebody, some random person left a comment on the YouTube video and said, hey, what you said is not quite right about the brute force algorithm for the traveling salesman problem. So I'm going to try to correct myself. I said last time that the brute force is very inefficient, right? And it's true. This is very inefficient. And I noticed, or I mentioned, inefficient. Sorry, I can't spell and speak at the same time. Very inefficient. And this is why nobody uses it in the real world, even if you're using a computer. It takes basically if you have n vertices, it takes n minus 1 factorial steps, which is way too big to use in real life. And I said there is no known better procedure, and if you can find a better procedure, then you will instantly become world famous, at least among mathematicians and people and corporations who want to solve this problem. What I just said is not quite accurate. What I just said, and I will say again, is not quite right. There is no known better procedure. Actually, there are better procedures than the brute force that are known, but they are still too hard to do in real life. This is what I said. So I'm going to say it this way: some better methods exist. This is what I said wrong last time. Some better methods exist to find the best possible route, which do not require a factorial amount of steps. That's the real problem with the brute force. But they still require an exponential amount of steps, which is still basically unworkable in the real world. So some better methods exist to find best possible route. They are, if you really care about the details, and this is what the YouTube commenter was trying to be very specific about. These better methods are exponential rather than factorial, which is better. Not a whole lot better, but in terms of usability, it is better, although still prohibitive. Exponential, sorry, this is hard to read. Exponential rather than factorial. All right, some better methods exist to find the best possible route, but they are still unworkable in the real world. I will say still inefficient. And it is still true what I said before. If you can find a really substantially better algorithm to solve the traveling salesman problem, you can become famous. You would immediately become famous among mathematicians. Probably not among ordinary people. All right, so this is my little correction of myself. Any questions about that? I don't know if anybody here cares about the distinction, but if you're out there, YouTube commenter, I hope I said it right this time. All right, great. Feel free to check out the comment below, like and subscribe. if you want compelling antiviral content. What I want to talk about today, so this is a little list of the techniques, right? There is the brute force method, which does always give you the right answer, but is basically unworkable for realistic, real-world sized big examples. We also have the nearest neighbor algorithm. And we also have and what I call the repeated nearest neighbor. This is what we did last time. And I will say this is much more efficient. You could easily do an example of this by hand for say 10 vertices, which would be totally impossible to do with the brute force. Much more efficient. The problem with this is, doesn't always give you the best route. But in real life situations when the brute force is unworkable, you have to settle for something which doesn't always give you the best answer. And the nearest neighbor is one such procedure. It gives you something which you hope is going to be close to the best answer, but is not guaranteed to be the best answer. And what I want to do today is another one. This is called the sorted edges algorithm. And it is the same as what I said about the nearest neighbor. It is also much more efficient than the brute force. You could easily do a big example by hand, and we're going to do some examples by hand, of course. Everything we do is by hand. So this is also efficient. But doesn't always give the best answer. So it's just like the nearest neighbor. I mean, you do it differently, but the reason it exists is as a more efficient alternative to the brute force, but still doesn't give you, doesn't always give the best route. And just because sorry, I'm just now realizing that I forgot to do something. And I'm going to cut this out of the YouTube video because they're going to pause and read my texts. Okay, the sorted edges algorithm is what I want to talk about. All right, it's fairly easy to do. I mean, just like the nearest neighbor algorithm. Remember, the idea for the nearest neighbor is you start somewhere, and then from there, you choose the cheapest edge every time as you go. The sorted edges is like that in that it involves choosing the cheapest edge over and over again, but you don't decide to start in anywhere in particular, and you don't try to choose the edges in a path as you go. Where's my paper? So here's how we do it. We are going to begin by write out the weights in increasing order. I tried to do this so you could just write this right on the paper that I just handed out. Although I don't know if you write smaller or bigger than me. Write out the weights in increasing order. So when I see the weights there, I see 2 1s, and I'm just going to write them down. 1, 1. There's a 2. I think there's only 1 2. There looks like 2 3s, 2 4s, 2 5s, and a 7. All right. Make sure you get them all. When you are looking, you have to. I suppose you have to look a little bit carefully, make sure you aren't missing any. This is why it's called the sorted edges. I have written the list of edges, at least the weights, in order. That's the word sorted. They are in ascending order. And you look at this list now, and you just pick edges from here, starting with the cheapest, starting with the least weight. So rather than choosing a starting point and going from there, which is what you do in the nearest neighbor, you just look at the whole list at once and you say, all right, I definitely want this one. I definitely want this other one. And as best as you can, you try to pick the ones that are the cheapest overall. And then see if they will actually assemble themselves into a circuit. That's the idea here. So you're going to pick edges starting with the least weight. And let me just say parenthetically, don't worry if they are connected to one another or anything like that. Don't worry where to start or if they are connected. Like in this example, you can see the two edges with a 1 on them are not even, they don't even meet up, right? Like this is one of the ones and that's another one of the ones. But we don't care. When we're doing the sorted edges procedure, you just say, I want those two edges, regardless of if they actually go together in any sensible way. All right? Don't worry where to start or if they are connected to one another. The only rule is, every time you pick a new edge, you have to make sure it doesn't make a subcircuit and it doesn't have three chosen edges meeting, because as we all know, those things are illegal for a Hamilton circuit. So I'm going to say never make a subcircuit. These are the same rules that we've always talked about concerning Hamilton circuits. Never make a subcircuit and never choose 3 which meet. But otherwise, you just keep on choosing edges, and eventually you will choose enough to make a Hamilton circuit. So let's just see what happens in this particular example here. And I'm going to try to write my answer down here. All right, like I said, I look at the list of numbers and I want the smallest number. So I choose the 1 here. I'm going to choose both of the ones. They are here and here. All right. They don't go together really, but they will eventually. Next, I look at the 2. I ask myself, can I include the 2 without violating these rules? I'm not allowed to make a subcircuit. I'm not allowed to have 3 meeting at the same point. I think the 2 is legal. That's this one here. If I fill that one in, it still doesn't make a subcircuit, and I don't have 3 which meet at the same point. So the 2 is still allowed. All right? I'm just going to go down the list here. I will use them all if possible, and if not, I have to skip over them. So how about the 3s? There's 2 3s here. I have this 3 here. I think that one is not allowed at this point, because that will close this off and make a subcircuit when I haven't hit all the vertices. So I have to exclude that 3. I'll sort of X that out. What about the other 3 is here? Is that one legal to do? No, that would make 3 meet over here. So I have to exclude that 3 also. And so on. You just go down the list here. How about the 4s? I have 2 4s. There's one going here. And one over here. I think that one is illegal from E to D. That would make 3 meeting down at D. But the other one is okay. I can do this one. So one of those 4s I'll use. I can't use the other one. In my list there's no real way to tell which 4 is which, but that's not so important. All right. Now, actually, you can tell. I mean, you can look through the list one by one, but you can tell actually there's only one way that's going to legally finish this up here, and it's using that edge right there, which is the 7, unfortunately. So these 5s will be excluded, and I choose the 7 like that. And this is how you do the sorted edges procedure. You do the edges in order from cheapest to, from best to worst. All right. Let me just say, in conclusion here. Right? The answer, starting from wherever you like. Starting from where you want. So, now in this problem, I didn't say specifically, find me a circuit which starts at B, but if I did, so for instance here, if it said, use the sorted edges to find a circuit at B, then I would take this answer. This starting point of B had nothing to do with the whole procedure. You ignore the starting point when you're doing the procedure. It's just at the very end, I can write this as if it was starting and ending at B. B is right here, remember? This is B. So this would be B, and then you can also choose either direction. You always get sort of two matching answers, one and its reverse, and both are correct. But I will choose, let's say, go down to C first. So this would be B, C, E, A, D, B. All right, I'm just writing that circuit letter by letter. And I started at B just because the question said so, right? You do not start at B when you're actually doing the procedure. It's only when it comes time to write the answer down. If it said start at B, then you write it down starting at B. All right? Any thoughts about that one? All right, let's do the next one. I'm going to do this next one all together, and then on the back of the paper is one for you to try. This one says, use the sorted edges algorithm to find a good Hamilton circuit starting and ending at A. Remember what I said. You do not care at this point where it says to start. That's only when you write the answer, you're going to write it as if it started at A. But when you're doing the algorithm, you don't start in any particular place. You look at the edges. So I got 2 1s. I wrote this down. 2 1s. I think there are 2 2s. 2 3s. Looks like 2 4s and a 5. Nope, 2 5s. I think there's 2 of each, right? Once you know what you're doing with these, you can probably do this in your head. You don't have to write down all the numbers. If you can keep track of, just look everywhere on the picture and find the smallest number and pick that one first. All right? So I'm going to pick the 1 first, and I can just start writing my answer here. In fact, we can choose both of the 1s. One of them goes down like that, and the other goes across like this. Right? Those are the 2 1s. Next is the 2. I want to use a 2, just make sure that it doesn't violate any of the rules. The 2 up here actually is legal, so I'm going to put that one in. And the other 2 is the 2 down here. That also is legal at this point. So I'm going to choose the other 2 also. All right, I picked both of the 1s and both of the 2s. They all fit in nicely. There's no problem about making a sub-circuit or having 3 that meet. And now actually that I've chosen, there's only one more edge that I need to choose, and there's only one way that you can do it, right? It would be to close it off by connecting the 2 at the bottom. That happens to be one of the 5s. So if in this example, if you had actually thought it through, you would have excluded all of these other ones for one reason or another until you end up with the 5 at the end. All right. And how do we write our answer? I said, now is the only time when it matters. I said the circuit should be starting and ending at A. So when I write it down, I write it as if I'm starting at A. So my answer is A followed by, and now you can go either way. I'll go to B next. And then it's E, D, C, A. Looks like some folks have some questions. Anybody? I'm about to tell you to do one, and I'm going to walk around so you can ask me your questions individually. Yeah?
Would it only be a sub-circuit if that, for an intersection had...
Oh, yeah, maybe. Are you concerned that this is a sub-circuit here?
Yeah.
Yeah, that is not a vertex there, so that doesn't count as a sub-circuit. This is a good question. These are, the only vertices are on the outside here. This right here is not a vertex. All right, let's try the one on back. We got 10 minutes. I think we can handle that. So on the back, I said, I wanted you to compare, see how you like it. Do it with the nearest neighbor, and then also do it with the sorted edges. Just so that nobody's confused about, isn't this the same as the procedure we did last time? It's actually not the same. See what you think, and I will walk around and see how you're doing.
Okay. Oh. So what did I Ah, okay, here's a 14.
How's it going?
I'm just going. I just feel like this is not right.
Choose the one first.
Yeah.
And then 7?
Yeah. And then I went to the E, and then I went to the 9.
Yeah.
I messed up the E though, so I have to read it. Like, oh, it's right there.
Yeah, you have to stick with it. Like in the example that we did before, I took some and I said I can't use some. That's how, as you go, some of them.
That's not, which one, that's like this over here.
Oh, I'm sorry.
So I just have to add this one.
Yeah. I was reading yours.
Just describe what you feel like.
No, I'm.
Okay, so if you're
Oh, that
doing
comes
Yeah.
there.
the nearest neighbor, you have to start at A. And then each step, you choose the cheapest edge available. From here, which is very different. You start out east. Doing okay? Different answer than what I got. Oh no, that's the sort of that is what I got. Doing all right? Yes. Yeah. Great.
Oh, for that one? So it says.
Like this is illegal.
Yeah, so I
It's legal, but it's not.
Oh gosh. I'll try and work it out.
But then it's like, it's the same backwards. Okay, so that's when you write it? Because either one you do is the opposite backwards, so it doesn't. Okay, so then after, so I go A, F, no. Yeah. Oh, okay. Yeah, so I go A, F, C, D, E. Thanks guys. And then put the A at the end. And then A at the end. And that's for sorted edges. I don't know how to do yours. I don't want to actually hear, so.
We got to go in a few minutes. Let's talk about these. Sorry I didn't get around to chat with everybody. So let's do the sorted edges first, just because that's what we're talking about. You can write down all the edges like I did in the other examples, or you can just try to kind of choose the edges in your head. You want to start off by choosing the cheapest one, which is this 1, right? So I should take the 1, which goes across the top. Next, I look at all of these numbers here and pick the next lowest one, which I believe is this 7, right? So I also am going to take the 7 here, which goes like that. all of the numbers which remain, it looks like 8 is the next lowest one, and I should take the 8 if I can. That would fill in here, which is legal so far. I hope everybody's with me so far. Next, I look for the next lowest number, which would be a 9 here, and that I can fill in right there. I feel good about this. There's still no subcircuit and no 3 edges meeting at a single point. I'm good so far. What's the next number to choose?
14.
There's several that are lower than what she's saying, but for instance, the 10 here, you should consider the 10, but that would go here, and that's not allowed because that's making 3 meet here, and it's also making a subcircuit. So don't pick the 10. We have also this 11 on the bottom. That would also make a subcircuit here. You cannot choose the 11 here. What else is there? There's a 12 here. This is the 12, but that would make 3 meet, so the 12 is out. There's a 13 vertically here. We cannot do that. Would make 3 meet at the bottom. There's a 13 over here, which would make 3 meet at C. I believe 14 is the next one that is legal. All right. And now there's only one edge missing, and there's only one way to fill it in that completes the circuit. It's like this. So I picked the 14, and I ended up picking that 15. So this is the sorted edges result. All right. And I said starting at A, so I'm going to write my answer as if it starts at A, which is here. I'll go A, and then down to F, and then around C, B, D, E, back to A. All right, that's the nearest, no, that's the sorted edges. All right, the nearest neighbor, can we do it in 1 minute? I have totally defaced my picture here. It's all right, I have the picture on my paper. The nearest neighbor, starting at A, it means you start over here, and each time you choose the cheapest option. So, looking at my paper, starting at A, I see 8 is the cheapest option from there. And now I'm down at E, and I want to choose the cheapest available edge there. I've already used the 8. I think the next best would be the 11 going across the bottom. All right? So I choose that edge going across the bottom. Now I'm at vertex F. I'm looking at my paper here. I see a 9 going back to A, but that makes a subcircuit, so I'm not going to do that. I see 7 going diagonally up. That is going to be my best bet. All right? From there, I see a 1, which is definitely a good idea. And now from here, actually, there's only one way to go about it. I have to go across there and over there. So this was the nearest neighbor procedure. They are quite different procedures. All right, that's it.